Hello, future breast imagers. We're going to leave the patient for a while and talk about the equipment that we're going to be using. So we'll move from the art of positioning into more technical matters and talk about mammography machines. We're going to talk about the various components of the mammography machine and what their purpose and function is. Discuss special features and benefits for the mammography tube design, and talk about special requirements for proficient use of the mammography machine's photo timer, and then the rationale for the design behind the digital detector in mammography. So let's just go back and review what we learned back in our early chapters. What has gone on over the 4 decades of development in breast imaging. So 1970s really marked the period of dose reduction because of the use of dedicated machines and the single emulsion film and single intensifying screen combination that was developed by DuPont and then further perfected by companies like Kodak. In the 1980s, the dedicated equipment or the dedicated mammography machine really moved into the next era where zero mammography went away and was replaced by the dedicated mammography machines, which was started by CGR, the French company, and then more refinement to our films, our film screens, and processing dedicated processing of the film. 1990s introduced the quality assurance to improve and standardize quality across mammography centers and set expectations for mammography centers to be able to provide. And this was all made possible by the work by the voluntary MAP, Women's Health Equity Act, MQSA, and so forth. And then in the 2000s, where we are today, we're seeing the technological advancements with 2D digital mammography when we moved from analog to digital, and now into the world of breast tomosynthesis, which we call 3D mammography. I want to talk a little bit more about the 1990s and the quality assurance and how that came about. So in the 1980s, when the general X-ray and xerography techniques were replaced with the dedicated machines and low-dose film screen, although the benefits of screening mammography were showing some good results, what was noticed is that the quality across facilities was very different, and therefore even the doses were very different. So in 1985, the Nationwide Evaluation of X-ray Trends, NEXT, evaluated dose and image quality at 230 facilities in the United States, and they found that only 64% of facilities had acceptable processing conditions. So with this notice that the ACS then implemented the National Breast Cancer Awareness Screening Program and began then the mammography accreditation program to ensure image quality. Now the MAP program was voluntary, but it showed that people were interested in providing quality. Facilities wanted the voluntary accreditation through the MAP program because they could tout that, and it could be an edge in marketing for their services. But when the Women's Health Equity Act was passed in 1991, the Mammography Quality Standards Act became a reality in 1992, and this is where it was required for any facilities in the United States that were going to offer screening mammography had to meet the requirements of MQSA and prove their credentials before they could have a mammography program, and to maintain those quality levels through their daily, weekly, monthly quality assurance and inspections that happened on a continuous basis. You can see on this side how the radiation dose to patients varied during that time from 26 to 260 millirads per view at facilities. 41% facilities demonstrated unacceptable variation in film processing conditions. Film processing was probably the Achilles heel for many of the mammography facilities. It was hard to maintain good processing conditions until people went more dedicated processing for mammography. We were fighting a lot of processing artifacts. So in 1992, the Mammography Quality Standards Act was signed into law, and that act regulates the mammography machines. It regulated the processor performance, which now it's regulating our image cycle from the capture of the image to how it's displayed for the radiologist. Our phantom images, which are used for quality control, our clinical images, and the dose. So in looking at the mammography machine, the part of the mammography machine where the patient is positioned is the gantry. And this is also sometimes called the C-arm. It'll move 360 degrees. It's going to consist of its main components, which would be the X-ray tube, a face shield to help keep the patient's head or facial structures from shadowing the breast, the electronic controls that you see on the side there to move the C-arm, the compression device, which the compression device come in various sizes and shapes, the breast thickness indicator, the automatic exposure control, and then the digital platform, which is your digital plate, and your foot pedals. So the part of the mammography machine where the technologist has control over the exam is the computer monitor, which is either going to be a 2 or 3 megapixel. It's not a diagnostic monitor, but it's an appropriate monitor so that the technologist can see the image immediately after the exposure is done. So she will know if she needs to do additional views or retake the image. The modality work list, which is going to be the work list that populates from the PACS that shows the patients on that list. The automatic exposure controls, that's true with any X-ray machine. The ability to change technique, change density, and then the radiation barrier that she's going to stand behind. So the mammography machine generator, the generator of a mammography machine is going to want to use the most usable part of the waveform. And today, what they use are constant potential generators because they produce less than 13.5% ripple. And you can see by looking at this diagram here that the less ripple is what you want, and so that would be your constant potential. The ripple is going to run less than the 13.5% depending on the manufacturer, and then the KVP selection depends upon the amount of ripple. Just keep in mind that the less ripple, the less there's going to be variance between what your KVP setting is in the generator and what the KV truly is, depending on the ripple. So for example, if you have a 25 KVP setting at the generator and you have a machine that produces a 5% ripple, you're going to be very close to 25 KVP in the exposure at 24.4. But if you jump up to, say, a three-phase generator with a 20% ripple, it's going to be 22.5 kV. So you want to look at table 11-4 on page 392. Oh, here it is right here. So here's what I was talking about. So the lower the ripple in the waveform, because of the constant potential generator, the more efficient the kV is going to be that actually exits the tube housing to then penetrate the patient. So it's the efficiency of the unit. Analog mammography, the photoelectric effect results in characteristic radiation, and this is what works best in mammography. The radiation emitted by the tube is homogeneous, and it's best used with the type of target materials that the analog units were built with, which would be the molybdenum and the rhodium. And depending on the patient's size of breast and density of the breast tissue, if the breast is compresses less than 6 centimeters and is not super dense tissue, then the Molly tube would be used. If the patient then moved to over 6 centimeters of compressed tissue and it was very dense tissue, then the rhodium would kick in. Rhodium was better at a higher kV range for that penetration. Now, with the development of the digital mammography, we've switched to the tungsten target tubes. With analog, these tubes were unacceptable because of the atomic number, and the characteristic peaks of the tungsten were well outside the preferred kVp range in which the photoelectric effect predominated. But with the uncoupling of the kVp and contrast in a digital machine, most manufacturers have switched from the Molly-Rhody target tubes to tungsten. One manufacturer, because of the design of their digital array, continues to use Molly-Rhody target tubes with their 2D and 3D machines, but the others have switched to the tungsten. There's a new way to deal with the contrast in digital, and that's using the window width and window level. Traditionally, the kVp would control the contrast and mass would control the density, and what we got is what we got. But now there's the ability with digital to do some post-processing, either with algorithms in the machine or at the workstation by the radiologist and or technologist to deal with the densities and with the brightness control, and to window and level the contrast and so forth. So the kVp is controlling the penetration or the photons needed, but digital imaging is using a higher kV setting because kVp no longer controls that grayscale, thus resulting in a lower dose to the patient. So contrast is still very important in mammography because a cancer is going to show up white or a mass is going to show up white, and if it's hiding in glandular tissue, that's white. So it's hard to find white in white. And the more contrast or the more levels of gray that we can see, the easier it is to differentiate things within those white bodies of tissue. Any method that improves contrast on a mammogram is desirable, and those two methods are the use of specially constructed mammography grids and the compression of the breast. Compression of the breast is very important. It's one of the first things that a technologist, when they're learning, is afraid to really be robust with because they don't want to hurt the patient. but it's important to learn proper ways to compress because this is what really spreads that tissue, allows proper penetration of all the tissue that's in the breast. So it's important to really understand the importance of the compression. So the methods to control scatter, as in any other X-ray unit, is the use of grids. They increase contrast by reducing the scatter, the unwanted X-rays. And the mammography grids are soft. They're like a pliable grid with a grid ratio of 5:1. Breasts do not create scatter to the same degree as a bone or a thick body part like your abdomen or pelvis, so a soft grid suffices for mammography. So you can see by looking at this here, you can see how compression will control the scatter, therefore improving our contrast. The less scatter, the less meaning that we're getting better contrast. So there are 7 reasons to compress the breast, the reduction in scatter being one of the 7 reasons. So those 7 reasons for compression are to decrease motion and unsharpness, decrease geometric unsharpness, meaning getting everything as close to your imaging plate as possible, to increase contrast by eliminating the scatter radiation, to separate that glandular tissue so we can eliminate as much summation of tissue as possible, reduce noise, create a more uniform density, and to assess the density of masses. So let's talk about the special conditions of a mammography tube. So the mammography tube is specifically designed for breast imaging in a mammography X-ray unit. So what they have done is, because X-ray tubes, X-rays come out of the X-ray tube in diverging pattern, the mammography manufacturers have reduced this diverging field along the chest wall. So they don't want to unnecessarily expose lung tissue, beyond the chest wall of the patient. So they've reduced this field along the chest wall, as you can see in this diagram here. It reduces the field of view by about 40% of the entire diverging field. So to regain some of this lost exposure field, the X-ray tube is tilted inside the tube housing so that the chest wall ray is perpendicular to the chest wall edge of the image receptor. So I think that this shows real well what happens. And the other thing too is, because the most useful part of the X-ray beam is going to be hitting the thickest part of the breast, which is against the chest wall. So the focal spots are made, the smaller the focal spot, the better the resolution. When the first dedicated mammo machine was built in 1965, the X-ray tube designers realized in order to find breast cancer earlier, better resolution was required, and therefore the smaller the focal spot size, the better the resolution. So most X-ray tubes are going to have 2 focal spot sizes. The typical focal spot is going to be 0.3 millimeters in a mammography machine, and the smaller is going to be 0.1 millimeter, and that is the one that would be used when you move to magnification. The magnification, increase in magnification resolution is necessary because of the part being so far from the image receptor to get that magnification. Most magnification platforms are either going to be a 1.5 times magnification or a 2 times magnification. The image is larger, but has less resolution, so you want that smaller focal spot. So here's just talking about how the mammography heel effect works in X-ray tubes. The heel effect is used in mammography. It is oriented from the chest wall to the nipple rather than left to right field as in diagnostic radiology, because the heel effect, we want to take advantage of that at the chest wall, which is the thicker part of the breast. So computerized assisted detection, or computer aided detection, is a spell checker in mammography. And what it does, and used to be that there were these standalone units, and you'll see this in your book, where when we were analog, you would run the film through the CAD system, and then there would be an image presented or a film produced that had these little markings. And if you look at this little image here, you can see where the left CC has the little like X, kind of an X with an extra line through it. And then the right MLO has a little triangle. Those different markings mean different things. So depending on the manufacturer, the X may be saying, hey, this computer thinks that there may be a mass here, check this out. Or the triangle may mean, hey, the computer detected some calcifications, check this out. Or the computer sees an architectural distortion, check this out. So nowadays, it's all built in to your network, your CAD does. It comes with your mammography unit, and everything happens, behind the scenes. There's no specific additional unit that you have to run anything through. It's included in your networking when you set up your digital mammography. So it acts like a spell checker, and those results are going to display at the radiologist's monitors. They can turn it on and off, and it detects, it does not diagnose. So just like I said, it's going to make these little marks. And then the radiologist can look at that and go, yeah, I picked up all those, or hey, wait a minute, I didn't really notice that. Let me take a closer look at that. So that's what computer assisted detection is. Not a computer assisted diagnosis, it's computer assisted detection. So that kind of wraps it up for this chapter. We're going to get a little bit more into the equipment in chapter 12. And so if you have any questions or you need any additional information, always feel free to reach out to me via email or a phone call. I'm in the office usually every Tuesday from about 10 a.m. until 2 or 3 p.m. And if you let me know ahead of time, I can always meet with you there. So make sure that you just reach out to me and let me know. Okay, thank you.